the main new results of this talk. It is joint work with Peter Gordon. And the goal of this talk is to explain two theorems with certain background. First, I will introduce and characterize certain apparently new class of metrics on octonionic plane, Riemannian metrics, which are octonionic analogues of Kähler metrics. And then I will present certain version of octonionic version of Calabi-Yau type theorem for these new metrics, which is a kind of Monge-Ampere type equation, and which we can prove existence of solution under certain assumptions. Okay, and so these are two main results. But before I will go, I should say that all equations will be for two octonionic variables. And before I will go to this rather specialized new case, let me say a few words about how it fits into some more general context. What is the motivation, what are more classical results, and what are more recent related developments which somehow motivated this direction. First of all, real and complex Monge-Ampere equations are very classical, very well studied. There is a huge literature which one cannot serve in such a talk. And let me remind you briefly what it is. Both real and complex Monge-Ampere equations exist in several modifications, but generally they look approximately as follows. Over real numbers, it is determinant of some real Hessian in local, I write in local coordinates. We take real Hessian of certain unknown function plus some matrix Gij, which is usually symmetric. And this should be equal to the right-hand side, which depends on x, u, and the gradient of u. F is a certain function. Usually, one assumes that this matrix is symmetric, and usually positive definite or zero, depending on the context. Real Monge-Ampere, complex Monge-Ampere equation looks formally quite similar, except that instead of real Hessian, one takes complex Hessian and adds some Hermitian matrix. This bar over the second index, it is just traditional and complex geometry. So this is Hermitian. Positive definite usually or zero. So this, okay. Usually one makes some extra assumptions on initial data or on the unknown function to make this equation elliptic or degenerate elliptic. Also in some geometric applications, this assumption might be unnecessary, but the methods work well under ellipticity assumptions. Both real and complex Monge-Ampere equations appear and were used in several geometric applications. For example, real Monge-Ampere equation can be used to prove existence of convex hypersurfaces with prescribed Gauss curvature. And another different application of real Monge-Ampere equation is optimal measure transportation problems. Okay. Complex Monge-Ampere equation, its geometric applications are very different despite formal similarity. One of the most famous applications of complex Monge-Ampere equation is theorem of Calabi-Yau, or another result, Calabi-Yau, proof of existence of Keller-Einstein metrics on complex manifolds. From the analytic point of view, to study real and complex Monge-Ampere equations, they have in common a lot of common tools. For example, a series of general elliptic equations applies in these two cases, and furthermore, some more specific methods to deal with Monge-Ampere equations apply often in both situations. For example, some methods, like Pogorelov method to get second-order estimate, was first developed for real Monge-Ampere equation. Then, with some modifications, it was applied in complex Monge-Ampere equation, like Calabi-Yau theorem. Okay, this is what I call classical cases. In the last approximately 20 years, there were a number of attempts to understand how far the common tools in real and complex case can be generalized further in new context and applied to new equations. And in this process, of course, there were developed some new tools, and this includes Monge-Ampere equations as well as closely related theory of plurisubharmonic functions. One of, in fact, several most general approaches in recent years were developed by Harvey and Lawson in numerous papers, which deal with plurisubharmonic functions in new contexts, which are generalizations of convex functions, for example, or complex plurisubharmonic functions, and Monge-Ampere equations. Another approach in another development was introduced by myself about 2003 to study, where I introduced Monge-Ampere equations over quaternions on flat quaternionic space. And okay, today I'm not going to discuss this case. This is over quaternions. And this approach partly overlaps with Harvey-Lawson theory. And later, from flat space, the approaches were general. The notion of Monge-Ampere equation plurisubharmonic function was generalized to hypercomplex manifolds by me and Misha Verbitsky. It is, again, hypercomplex manifold is, again, manifold with certain quaternionic structure. Okay, but today I will not discuss quaternionic case.
Is it possible to give any specific examples of capital F for the matrix GRJ? Is that helpful? Classic examples of what?
I will discuss it in complex case. In a little while, will I formulate complex Calabi-Yau theorem? I will state it explicitly.
I see. So for the purposes of that theorem, there is particular F and particular G.
Yeah, in Calabi-Yau theorem, Gij is just scalar metric, and F is just certain positive function which depends only on the coordinate, independent of this. Okay, so let me discuss octonionic situation, and for this case also there is some kind of theory of plurisubharmonic functions, very basic one so far, which also can be obtained for Harvey-Lawson approach. Okay, so we have, let me remind some basic algebra of octonions. So real numbers are embedded into complex numbers. Furthermore, they are embedded into quaternionic field, which is non-commutative but still associative, and quaternions have dimension 4 over the real numbers. And quaternions can be embedded in larger field of octonions, so which have dimension 8 over real numbers. They are neither commutative nor associative. Despite maybe on the first glance they might look as a very exotic object, they appear very often in various classification problems in Lie theory, symmetric spaces. Usually, in order to describe some algebra of octonions, one uses certain bases of 8 elements. Which satisfies the following properties: E0 it is just 1, EA square equal -1, and any octonion Q can be decomposed with respect to this basis with real coefficients. I will denote in this talk standard notation conjugation of octonion, which is very similar to what we have in complex numbers. It is x0 minus the rest. Another thing which I will use in this talk, and it is important property of octonions, that if we introduce the following Euclidean norm, it is multiplicative. Okay, so there is, of course, it does not characterize product in octonions. There is some multiplication table for this basis element, which I will not write down explicitly. Okay, this is, okay. Now you see, in order to write classically in real and complex cases Monge-Ampere equations, it is done in 2 steps. First, one should know what is Hessian, real or complex, and then take a certain determinant of it. As a side remark, let me mention that over quaternions, the construction is the same. One defines first quaternionic Hessian, then takes, it is a quaternionic matrix, and then one uses certain non-commutative determinant, which is defined only on Hermitian matrices, which is called Moore determinant, and the theory works with this notion. Perhaps Moore determinant is not very well known to broad audience, but on Hermitian quaternionic matrices, it has all algebraic and analytic properties of usual commutative determinant on Hermitian, complex Hermitian, or complex or symmetric real matrices. For example, Sylvester criterion of positive definiteness and number of other standard properties. Okay. So over octonions, I want to define now what is octonionic Hessian. And for this, let me introduce first analogues of Cauchy-Riemann operators, which are, in this case, are defined in a rather straightforward way. So if we have sufficiently smooth function of one octonionic variable, the construction I'm going to give works for any number of variables, in fact. Then we define df by dq bar, where by definition it is sum from 0 to 7 e a df dxa, and similarly df dq is similar sum df dxa e a bar. So if you compare it to the complex case where sum would run from 0 to 1 rather than 7, these are precisely what we have in a complex situation. These are Cauchy-Riemann operators in complex case, but here we have to keep the right order. So here it is important that we switched the order in comparison to the previous line.
Is it anti-commutative, the multiplication on octonions? Does you get a minus sign if you switch the order?
No, it's more complicated. And now let me introduce octonionic Hessian.
So if you have a purely imaginary, if you have two purely imaginary ones which are orthogonal, then they're
purely imaginary, yes. Assume that we have real valued function which is smooth, twice smooth, for example, of n octonionic variables. We define octonionic Hessian to be the following matrix, n by n matrix, okay, so well, let me mention, so we like in all other cases, we apply certain operator of order 2, which is a composition of two Cauchy-Riemann operators. And it is not hard to check that on real valued functions, these two Cauchy-Riemann operators commute, so it doesn't matter in which order you apply them. So, okay, and now in order to define Monge-Ampere operator rather than Hessian, we need a notion of determinant. So this matrix is octonionic valued, and it has the following extra property of being Hermitian, namely, like in real case or complex case, it is Aij equals Aj bar for real valued functions. Okay. Okay, so as I mentioned, in quaternionic situation, there is a very good notion of Moore determinant on Hermitian matrices of any size. However, I'm not aware of such a construction, such a determinant for octonionic Hermitian matrices of arbitrary size. More precisely, I know a certain nice construction of determinant of for n equals 2 and 3, and not in higher dimensions. Yeah, octonions are very specific, very special. Moreover, so for example, in these dimensions, there is a nice notion of determinant which satisfies Sylvester criterion of positive definiteness, which is a useful property when you discuss analytic applications. However, so we can define Monge-Ampere operator for 2 and 3 variables. However, for some technical reasons, we have to exclude case 3, because certain identity which is satisfied by this Hessians in all other cases, real, complex, quaternionic, and octonionic 2 variables, is not satisfied in this case, and we cannot say anything about properties of this Monge-Ampere operator. So I will focus only in this case. And let me explain what is the determinant in this situation. So I will denote by H2O the space of octonionic Hermitian matrices. Octonionic Hermitian matrices 2 by 2. And we want to define determinant on these matrices. And and here is a definition, which is very simple. So general octonionic Hermitian matrix looks as follows, where on the diagonal A and B we have real numbers, and outside of the diagonals we have a pair of conjugate octonions. So it is AB minus Q bar, which is also equal AB minus Q bar Q, because Q and Q bar are commute. They commute. In fact, Q bar, it is equal to norm of Q squared. They always commute, and it doesn't matter in which order we multiply them. So it turns out that this determinant has many nice properties, usual standard properties of usual determinant. It satisfies Sylvester criterion of positive definiteness. And we are going to use it for Monge-Ampere equation in a little while.
So in this Hessian, the diagonal entries will actually be the Laplacians on. So I mean, you're going to get you've got 2 octonionic axes, yeah, and a function on each axis. So there's a function on R8. The number that you would actually get in the Hessian would actually be the Laplacian of that restriction, right?
Yeah. Yes.
He's talking about the Hessian.
The Hessian. In the Hessian.
Hessian, yes.
The diagonal entries are real, and they're actually.
I checked it for 2 variables.
Yeah, but I'm just asking about the question about for one variable when you just say like the upper.
I understand. I think this is what we have.
Yeah, and then you have.
Yeah. Yes, that's true. Okay. And now let me go back to postpone a little bit the octonionic case, and as a motivation for our first main result, let me remind you what is so-called DDC lemma in complex analysis. Okay, DDC lemma. Well, it's just name. I will not spell out what is DC over complex numbers. So, assume that we have a smooth function, real-valued function u on Cn or, okay, on some domain, open subset of Cn, C infinity smooth. And assume we take its complex Hessian, which is by definition this matrix. Okay, so it is matrix-valued function. And the question is, which matrix-valued functions can be obtained, at least locally, as Hessian of some function? No, of course, it is Hermitian matrix, point-wise. And moreover, it is, if we denote this by Tij bar, then it is obvious that this matrix-valued function T satisfies d dzk Tij bar equals d dzi tkj bar. Okay, I write it, maybe in some literature people prefer coordinate-free way to write these equations. I prefer to write it in coordinates in order to emphasize analogy with other cases, in particular quaternionic, octonionic. So I will denote this system of equations by star. And there is the following theorem, which is classical, which is called DDC lemma. So let Tij bar be a smooth function in open domain with values in Hermitian matrices, C infinity smooth. Then locally Tij bar is equal to complex Hessian. Locally, it means every point has a neighborhood in which Tij is presentable as certain as a complex Hessian of certain smooth function. If and only if this system of equations holds. Okay, and we are going to generalize this theorem to octonionic situation, but before I will discuss it, let me have a remark that this, if these matrix-valued functions are positive definite, assume Tij is positive definite point-wise, then they define Riemannian metric in omega. And this system of equations star is equivalent this metric is scalar. Okay.
I mean, this is just an elementary lemma in complex analysis. You just need to
No, elementary. It doesn't require any big.
Hard one's the global one.
I think it uses exactness upon Corellium and exactness of the Dolbeau complex. Yes, that's all.
But local.
Yeah, so
Super.
the fact that it's true on balls or something, though, is less obvious. You get a little bit of Dolbeau homology.
Yeah.
You need to know that integral form.
Yeah.
Okay. Let me also mention that this theorem, DDC lemma, has real version where it is also elementary, but it was, nevertheless, let me mention that it was introduced by Cheng and Yau in this year in order to study real version of the Calabi-Yau theorem. And this theorem also has quaternionic version, which I'm not going to state explicitly due to me and Verbitsky, but the hard part actually is due to Banus and Swan, the hard technical part, and it is indeed, in quaternionic case, the known proof is much less easy. Okay. And now,
Andrew Swan, or?
yes. Okay, well, where is this? And now, let me state the first main result, which is the octonionic version of DDC lemma. So, we work with octonions in two variables. So, theorem 1, a smooth function Tij on domain in O2 to Hermitian matrices over octonions and then C infinity smooth. Can be locally given as Hessian of some smooth function, octonionic Hessian, use smooth, infinitely smooth. If and only if the following system of equations is satisfied. So the system of equations, I probably erased it, yes. I will write it, but it looks a little bit complicated, so I will just write it for completeness. It is not very important how it looks like. But it is very much similar to complex case, but written in real notation. And just one should keep the octonions on the right side. Oops. This is end. Well, just it's not very important.
So those subscripts read 1 bar 2 and 2 bar 2? I couldn't tell the first one.
Sorry?
I was thinking, what is sigma? I said.
Sigma?
No, which is two bar 2.
Yes, it is 2 bar.
And the other one is 1 bar. I was thinking it was T sub T, but it's.
Yeah, sorry. Yeah, so this is a system of equations which I will denote double star. So if you specialize this system to the case of two units, namely complex numbers, so sum runs from 0 to 1, it is precisely this system in complex case, but written in real notation. Okay, let me say just one word about what stays behind the proof of this theorem. The proof is not, I think, is not very elementary. Maybe some structures behind the proof should be understood better, but the proof is based on a combination of two main tools. The first is Ehrenpreis theorem from 61, I think. So he proved very general result about solvability of systems of PDE with constant coefficients. This one has constant coefficients, and his theorem essentially reduces analytic problem to some problem of commutative algebra to find some generators in submodule over polynomial rings. And then we have to find these generators. So in this case, we use just, luckily, there is a program called Macaulay 2, which has an algorithm to find generators and submodules. So it is not very conceptual proof. Okay, but this is what we have. And now, given this result, we can introduce analog of Keller metrics. Okay, so assume that we have a matrix valued function Gij on certain open subset of octonionic planes, yeah, with takes values in Hermitian matrices, and assume that it is pointwise positive definite. Then again, it defines at every point it defines Riemannian metric in the following way. If we have some vector from O2, which we consider it as a tangent vector at certain point, then we define square of its norm almost like usual, just xi bar, sum over I and j, gi bar j, xi j. So it should be positive, since matrix is positive definite, it's positive if xi doesn't vanish.
So what exactly is the meaning of being positive in octonionic?
Okay, actually this is a definition. That this expression, real part of this product, is positive for non-zero vector.
Is that the same as the diagonal interest is strictly positive and
Is the same as?
this diagonal strictly positive and determinant is strictly positive? Is that equivalent to that?
You mean Sylvester criterion?
Yeah, in octonionic.
Yes, yes, Sylvester criterion works here. Let me just mention that we have product of 3 octonions. In principle, I have to put brackets in some way, but since I take real part, one can show that it doesn't matter in which order I put brackets. Okay, so and now definition. So this metric, is octonionic Keller by definition, if and only if double star is satisfied. or equivalently, this metric is locally given by a Hessian of some function.
It's sort of dangerous notation, because if you did it for quaternions, there's already a notion of quaternion Kähler that wouldn't be this.
Yeah, absolutely. I failed to find good name for this metric. Moreover, it turns out that this name is already occupied over octonions. But okay, this is the first main result. These are octonionic Kähler metrics, and now I would like to go further and to introduce and to formulate the second main result, which is an analog of Calabi-Yau theorem. Okay, but first, since complex case serves as a motivation for our work, let me remind you the classical Calabi-Yau theorem. It will be instructive. I will formulate it in analytic form. Also, originally, the motivation to prove Calabi-Yau theorem comes from geometry of Kähler manifolds. Maybe I will state later the main geometric application of it. But the analytic form will be important for the rest of the talk. So let M be a compact Kähler manifold of dimension, complex dimension n, and usually connected. Let omega be the Kähler form. I don't want to define forms on this language. Maybe most of you know it, but later I will anyway reformulate the theorem in coordinates. Then the PDE, and F is smooth real-valued function on the manifold. Then PDE D DC F U plus omega to the power n equals e to the f omega to the power n has a smooth solution, has a C infinity solution, if and only if the following normalization property is satisfied: integral over the manifold e to the f minus 1 omega to the n equals 0. In this case, solution is unique up to an additive constant. Additive constant. Okay, it turns out that this equation is a complex Monge-Ampere equation, automatically elliptic, and let me rewrite this equation in local coordinates in order to compare to what was promised at the beginning of this talk. So in local coordinates, this is equivalent to the following. Determinant d2u dzi dzj bar plus gij bar equals e to the f, where gij bar, maybe f should be replaced by some shifted function. Maybe one should add some constant. Maybe I forgot the normalization. But what are these GIJs? In local coordinates,
You have to put also the determinant of Gij on the right-hand side.
oh, yes, thank you. Yeah, that's right. Thank you. It is I times Gij bar dzi dzj bar. Just local coordinate expression for the Keller form. Okay, and as a side remark, let me mention that the main application of this theorem, classical, is the following one. If one assumes in addition that first Chern class of the tangent bundle of the manifold M vanishes, then the manifold admits another Keller metric, which is Ricci flat. Okay. Now I would like to return back to the octonionic case and to state kind of version of this equation and this theorem in that situation. Okay, first of all, on what kind of manifolds one can write such equations. I wouldn't like, so far we can write it on rather narrow class of 16-dimensional manifolds, two octonionic variables, right? One can, for example, this class includes octonionic tori, where, so lambda, it is a lattice but formally the class is more general. Let me say by words what it is. Manifold admits atlas of charts such that all transition functions are first of all affine, namely composition of translation with linear transformations, but moreover linear transformations preserve the class of octonionic lines, namely they belong to the group which is isomorphic to spin 1, 9 times real numbers, which is certain subgroup of GL 16R. I really don't want to define this group. For such manifolds, we can write our equations. So tori are certainly of this form, because just translations are enough.
But you need to have a background octonionic metric. I'd be worried that you can have generalizations of Hopf surfaces here where the Calabi-Yau theorem makes sense just in the complex case.
Sorry?
So there are, if you were just to restrict it to manifolds that have an affine structure and are complex manifolds, then you have things like Hopf surfaces that don't admit a Kähler metric, and you can't do Calabi-Yau, the Calabi-Yau theorem on there because you don't have a background Kähler metric.
Yeah.
So you must have an extra hypothesis here that's saying that you have some
These are two different things. Let me explain. This is a good point. For such manifolds, we can formulate our question. We can write a Monge-Ampere equation. However, at the moment, we cannot solve it in this generality, and we can solve it if we restrict these transformations to smaller group, which is called spin 9.
Yes.
It is called.
Preserve the background attribute.
Yeah. There is a hope that there is the problem can be solved in greater generality. In fact, you see, okay, again, if you compare to complex situation, Kählerness of this form omega was important in the proof of in Calabi-Yau proof, original proof. However, there is work about 10 years ago of Tossati and Vainkov. They remove this Kählerness assumption. So this is analytic result about Monge-Ampere equations, where this form omega doesn't have to be Kähler. And perhaps, well, yeah, maybe. This is one thing, but what you ask now I start realizing that you asked in a different direction.
Well, I was just observing that, if you were just in the complex case, this is still be in a very, very narrow class of complex manifolds if you take things with affine structures. But the point is that among things that have an affine structure, there are lots of them that don't have geometries.
But do they have Hermitian metrics?
They have Hermitian metrics.
Yeah, I think for Hermitian, Tossati and Vainkov proved solvability.
They still need the omega to have some extra property. I think the Steno-Kähler, there's a weaker version of Kähler. They still need some hypothesis on the metric.
Oh, okay.
And,
okay.
I think that in yeah.
Okay, thank you. But anyway, we can prove, we can formulate the equation for such manifolds, and we can prove for such manifolds. Okay, so let me formulate the second main theorem. The equation. Sorry, I forgot some preparations. So we have, for simplicity, to avoid, for simplicity, I will work with torus. Just otherwise, this should not be functions, but some sections of some bundles. I want to avoid this background. So we have some smooth. C infinity smooth matrix valued functions, which are pointwise positive definite, and octonionic Kähler. Octonionic Kähler matrix, in other words. And let f be C infinity smooth function of this manifold. Then the statement is formally very similar. The equation equals e to the f determinant gi bar j has C infinity solution if and only if integral over the manifold satisfies similar equation d volume, which is just standard Lebesgue measure on the torus. For more general manifolds, which I briefly mentioned, also there is some standard, some measure, similar one. It should be 0, yeah. In this case, U is unique up to an additive constant. Okay, this is an analog of Calabi-Yau theorem. So proof also goes using continuity method and a priori estimates. Okay, but let me wait. But let me mention finally at the end that Calabi-Yau theorem, the classical one, has also a real version due to Cheng and Yau. And also they formulated a real version on manifolds with so-called affine structure, which I mentioned. Then all transition functions are affine. So in this generality, they can introduce real Hessian and real Monge-Ampere operator. And over quaternions, there is a conjectural version of Calabi-Yau, conjectural version due to me and Misha Verbitsky, which in 2010, which so far was proven in a number of rather special cases. And let me mention very briefly, also I don't state the problem, but nevertheless, let me say that I proved for flat, flat hyperkähler manifolds with flat structure in 2013. Then Gentili with Sony, they in 2000 they proved it for special class of 8-dimensional manifolds. And finally, there is another interesting case due to Dinev and Sroka and from 23. They proved it for Kähler manifolds, but with some, sorry, not Kähler, hyperkähler manifolds. But with some extra assumptions on the initial data. Okay, I will stop here. Thank you.
Questions?
So one part of this story, the class of manifolds where you can get a result, is that you kind of want a spin 9 structure. Right? And so it turns out that the manifolds with holonomy and spin 9 are actually all symmetric spaces. That was an open question for a while.
No.
But for example, there is an octonionic projected plane which has a spin 9 structure, and it's not sort of locally modeled on octonionic 2 space except at the infinitesimal level.
Right.
But I'm wondering if these kinds of equations would make sense there.
That's a good question, but I don't know. But let me say something analogous to your question over quaternions. So over quaternions, there are now all these results which I mentioned here. They are on they are in terms of hypercomplex manifolds. On the other hand, quaternionic projective space is not hypercomplex. However, for this space, I introduced, one can introduce analog of Monge-Ampere operator not on functions, but on sections of some line bundle. And one can prove several non-trivial properties like Alexandrov and Chern-Levin-Nirenberg type estimates. Regarding Monge-Ampere equation, nobody studied it. But I think one can formulate such a question at least.
Is that somehow basically a story about if you pass through the Swan bundle, which is hyperkähler? So over a quaternion Kähler manifold, there is this bundle discovered by Swan, which is a hyperkähler manifold, and perhaps, so if you have a function that's equivariant upstairs, you could think of it as being a section of a line bundle downstairs.
I formulated it in different terms, but for example, the Hessian on this space, it is given by what is called Boston operators, and one can define product to construct Monge-Ampere operator, like determinant. But explicitly, I did not use Swan bundle, but maybe. I just, I don't know.
So any hope you go beyond dimension 2?
Sorry?
Any hope you go beyond dimension 2?
As I said, in principle, one can formulate the problem, the Monge-Ampere equation, in dimension 3. But we cannot prove anything because the method doesn't work. In dimension even higher than 3, we cannot formulate the problem.